Mhm.
Yeah, but all right, so another 2 minutes.
Yeah, we'll start within a couple of minutes. Mm. Mm.
Yeah.
Mm. 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 I understand we'll be starting in 1 minute. Please put in the chat where you're dialing in from.
All right. Morning, good day, good evening to everyone. My name is Alex Belovic. I'm a petrophysicist based out of Malaysia. I'm on the SBWA Malaysia committee. We call ourselves FESM. Today we have a very interesting event, a bit unconventional. Steve Curry has kindly agreed to run this online masterclass. It's not something we normally do, but we thought it would be interesting to the crowd. And what's also unusual about this online presentation is that you will be able to get personalized feedback after the presentation. You may decide to share your data set, or may just decide to ask a question offline, and Steve would be glad to answer. So a very brief introduction. Steve Cuddy holds a PhD in petrophysics from Aberdeen University. He also holds a bachelor's in physics and astrophysics and philosophy. He writes AI software and has 45 years industry experience in petrophysics, working with companies like Schlumberger, BP, and Baker Hughes. Steve is the inventor of the fractal foil function that describes the distribution of fluids in a reservoir model. In recognition of outstanding service to the SBWLA, Steve was awarded the Distinguished Service Award in 2018. Steve is an SBWA Distinguished Lecturer for the 2021 season as well. Steve, the floor is yours.
Right, thank you. Could I have a thumbs up if you can see my first slide?
Steve, you're muted.
Right. Okay. Right. Thanks for coming along. The this masterclass is based upon a paper which I wrote, which won the Best Symposium Award some years ago. And based on that paper, I was asked to be a distinguished speaker for the SBWA. So let's have a look at the outline of this presentation. So the objective, the single objective, is for you to be able to derive a confident SW versus I function for your reservoir. I will go back to basics and I'll explain why we need an SW function for reservoir modeling. But very importantly, I want to discuss some definitions. If we can't agree on the basics, we won't be able to go anywhere. And these will include, as what you see on the screen there, the free water level, etc. After we derive the function, I will go into several case studies and applications. And after the masterclass, I am happy to work on your databases and give you personalized feedback. So why do we need a reservoir model? I show you a cartoon here of a reservoir model. It's like a Lego model with different cells, the red and the yellow. These different colors could represent different zones or different lithophases or different porosities. But what you have a model of cells, and you populate this model with water saturations and hydrocarbon saturations. You add up all the hydrocarbon saturations, and that gives you your hydrocarbon in place. You can also use the model then to put the wells in the best places in the field, and you could use this as a basis for simulation. Now, the model needs some key things. It needs to know what the fluid contexts are. The net reservoir cutoff is very important. And in this presentation, the SWI function. The wells are shown here in black. There are shown 5 vertical wells. And this is actually a minimum amount of information compared to the size and the volume of the reservoir model. So the challenge is to be able to populate this reservoir model based on the information from the wells. And that information is very limited and includes core and electrical log data. So we need this SWI function to initialize the 3D model with fluids. It tells us how the water saturation varies as a function of height above the free water level. Another definition that we'll come back to. It tells us in all those cells in the 3D model how the formation is split between hydrocarbon and water. And it tells us the shape of the transition zone. Now, a very good SDRI function requires that 3 independent sources of fluid distribution data are consistent. These are the formation pressure data, like for MDT, the electrical log data, and the core data. The model should account for varying permeability and fluid contacts. It must upscale correctly, and I'll explain that later. But importantly, it should be convincing to everybody, and it should be easy to apply. So this is the result of the presentation. This is where we're going. We're going to derive an SWI function. Now we'll go into the details. This function has often been called the BVW function or the FOIL function. And this is the function. Very simple. It says the bulk volume of water on the left-hand side is equal to, is a function of the height above the free water level with 2 constants. And the dimensions on both sides do match up before you ask. So this function is based upon BVW, the bulk volume of water, and is independent of porosity and permeability, as I will explain. But the key thing is your complete reservoir in the reservoir model is completely described by these 2 parameters. So let's have a look at where this came from. I'm going to show you a very difficult well. This data set was provided by the London Petrophysical Society, and it was a challenge. As you can see, it's a very heterogeneous formation where we've got varying porosity in this track here. We've got varying permeability in the right-hand track, and it's shaly throughout, and it is very complex. Now, the problem, what was noticed by one of the oil companies in London, was that SW actually increases with height. It's going up to 100%. Where normally we expect, as I'll explain, water saturation to decrease with height. So what this oil company did, they were very crafty. They challenged the community in London to see if they could fit a function to this, which seemed impossible. So there was a shootout between different functions, the Leverett J function, the Skelt-Harrison function, and many others. And the BV function was also put into this competition. And the check was to see what could give the best match between this SW, which comes from the resistivity log, and the function. Now, the function then will be applied throughout the complete field based on this well. So this is the result of the shootout, shown in red. Remind you, the black curve is the RT, the resistivity-derived water saturation from the Arch equation, showing a lot of variation, but the BVW function gives it a very good match. And it gives a good match through all the different lithophase types. And permeability is not required for this function. So it is defined by two parameters. So if we can predict SW this well, do we need resistivity logs? Well, we still need resistivity logs, but the point is, if you have a function derived from your best wells, which describes your water saturation so well, if in a well that resistivity log failed, would you go to the expense of running that resistivity log again if you're at a function which could predict water saturation this well? Now, I want to show you something quite interesting about this plot. Even though this heterogeneous formation varies a lot, one thing is not varying dramatically, and that is the bulk volume of water shown in white, which is down the right-hand side here. The bulk volume of water is steadily decreasing with height throughout the reservoir, where the other logs are moving around over the place. Water saturation is a percentage of a percentage, and we'll be moving away from that, where BVW is important. It's also important to notice that these intervals here, which I'll show you are non-net, the BVW is equal to the porosity. And that is very important in this masterclass. I will go through several definitions as shown there, as we need them in the masterclass. Now, the first one is the bulk volume of water. The bulk volume of water is simply the percentage of water in a unit volume of rock. So you've got your unit volume, you've got your matrix, which could be limestone, it could be sandstone, you've got the water, and then you've got the hydrocarbon. Now, BVW is what is measured by the electrical logs. The electrical logs do not measure SW directly. They measure the conductivity of the water in the formation, depending on its salinity. If you send some core away for core analysis, they do not measure water saturation. They measure the bulk volume of water expelled from the rock under different pressures. You can get SW afterwards by dividing BVW by porosity, I'll show you. So it's important that BVW is what we measure as petrophysicists and what we measure as core analysts. And it is what we're going to use in this SW height function. Now, a very important definition that we must all agree upon is the free water level. The free water level is an horizontal surface of zero capillary pressure. If you drilled a large borehole where you're sat now, this would fill up with fluids, with water, and it would fill up to the free water level. In a well, with a wide borehole, this is where the fluid will separate out, and it's the free water level. This is where is the intersection of the pressures. If you took pressures, formation pressures in your wells, notice they are straight lines, one for the aquifer, the water gradient, and one for the for the oil or the gas above the free water level. It's a straight line because the tool measures the mobile phase, and it is water below the free water level and hydrocarbon above. The free water level is also important for this is where whatever SWI function you use, it is the base. So you can't proceed without knowing the free water level. And I will show you how to derive that. I want to contrast that with the hydrocarbon water contact, which you can afterwards forget about. The hydrocarbon water contact is the height where the pore entry pressure is sufficient to allow hydrocarbon to start invading the formation pores. And this is dependent upon the local porosity and permeability. So therefore, it's a surface of variable height compared to the free water level, which is an horizontal surface, and it is defined by zero capillary pressure. So this is interesting, but it's confused as a reservoir modeler. So we always think of the free water level, not the hydrocarbon water contact. But if you do require it, I will show you later how we derive it. Now, let's look at some real data. This is where the problem is. This is what historically has been the problem with petrophysics. When we plot water saturation against height, we get this shotgun pattern. In this cross plot, you'll see lots of cross plots today. The z-axis is the porosity. So this teases out the problem. It shows us that for all these wells in this field, where we've got high porosities, the water saturations are over to the left and generally lower and asymptotic to the free water level. Now, as you move through the blue, the lower porosities, to the very low porosities, the data moves to the right, and more importantly, it is offset. So in low formation porosity formation, the formation can be fully saturated for hundreds of feet above the free water level. So the challenge is we need to be able to describe this so we can put it into our reservoir model. So this is what has been done historically. You notice that there are different colors with porosity. So the first thing that the petrophysicist thought and the reservoir modeler thought would be to let's do it by porosity band. Let's have an SWI function for every porosity band. And this is what they look like. And this plot was taken from a document sent to the government for a North Sea field. It was actually put in the proposal. Now, there are some problems with this. If you want to derive an SWI function for each of these lines, you'd have to have sufficient data for each of the porosity bands. You'd have to drill wells in poor parts of the field so you could get this curve here. Now, they're visually unconvincing because these curves, these are real curves, actually cross each other. So visually, they're unconvincing, and mathematically, they're incorrect. And also, before you can derive a curve for these porosity bands, you'd have to first define this offset for the pore entry pressure for the different porosities. So you can see this was a major problem. So this is our data set. We've got a shotgun pattern. We want it to simplify it so we can use it in our reservoir model. So the next slide is going to show us what happens when we change the x-axis, water saturation, to the bulk volume of water, the percentage of water in a unit volume of rock, what we measure from the tools. And this is what we get. All the data collapses to a single curve, and we see this on hundreds of fields. I remind you, the z-axis porosity. So whatever porosity you've got, they fall upon this line here. So this makes it easier for the reservoir modeler. So the bulk volume of water is independent of rock properties. Now, if you tell that to sedimentologists, they just won't believe you. So to prove it, the petrophysicists use a very powerful technique, and it's called a cross plot, as shown here. So you plot your SW against height, and the z-axis could be grain size, zone number, it could be permeability, and whatever they used, the z-axis will show that the data will overlie. So it's very easy verified by making this cross plot. So you go between SW and BVW to convince the team. Now, a very important definition we need is called the net reservoir cutoff. We need this before we can proceed. It's also needed, besides the SWI function, it is needed for upscaling the reservoir parameters. Now, it is very simply the proportion of rock that is capable of storing hydrocarbon. I'll show you some plots later. And it is relatively easy to pick because it is usually based on the porosity cutoff. Now, I want to contrast this with net pay. Some people think of net pay, which is the proportion of rock which can produce commercial quantities of hydrocarbon. This is the definition at the SPWL website. Now, this net pay is often used to select perforation intervals, and therefore it's quite valuable, but it's very difficult to pick. And in actual fact, it will depend upon the oil price, because it would vary depending how determined you are to produce the hydrocarbon, how many wells you drill, how you inject, and so on. So forget about net pay. For the reservoir model, we only need net reservoir, the portion of rock which is capable of storing hydrocarbon. Now, what does the BVW function tell us about net reservoir? It tells us that there's something very interesting. At a certain height or depth in the reservoir, say here, these two pieces of rock are in different parts of the reservoir, but at the same height above the free water level. On the left, the rock is averaging 20 porosity units, and on the right, it's averaging 10 porosity units. And as you'll see from the mathematics later, what happens is that BVW is independent of the porosity and is the same everywhere at that depth in reservoir. So where we got 20 porosity units of rock, this is the water here and the hydrocarbon. But as the porosity decreases, the water saturation, the water BVW stays the same, and the hydrocarbon decreases. Now, in this case, this plot gives us the cutoff. In this case only, the porosity cutoff is 9 porosity units, because at 9 porosity units, BVW is equal to the porosity. And I will show you this on one of our cross plots. So the net cutoff then is defined as a rock capable of ordinary hydrocarbon. It is very important for reservoir modeling, and it does vary depending upon the height above the free water level. And I will demonstrate this on the next slide. So on the right here, we've got porosity varying throughout the reservoir, and we've got the CPI, computer process interpretation, and we see the hydrocarbon, the oil, in red, and we see the water on the right-hand side. Now, the hydrocarbon varies a lot because it only can go into the rock, which the water doesn't require. So it decreases slowly with the height above the free water level. Now, at this particular here, shown by the top arrow, we've got low saturations of capillary bound water, and the hydrocarbon enters the smaller pores, as shown by the net flag here. So you've got hydrocarbon. Now, deeper in this section, you've got porosity here above the free water level, which is actually higher than here. Yet, this is non-net because the hydrocarbon cannot enter the formation. So there are 3 steps in the masterclass. The first step is to define your net cutoff. And this is done by this very simple plot of water saturation against porosity. In this plot, we've got many wells shown. And what we see is this characteristic pattern. We've got the lowest water saturations at the highest porosities. And as the porosities reduce, then we end up with less and less, the water saturation increases and less hydrocarbon. So you can actually pick it, your net cutoff, from this cross plot. So it's derived from this cross plot there. So in this example, the net cutoff is 5 porosity units. And the significance is that there's nowhere in the reservoir where you've got porosity of 5 porosity units or less that you get hydrocarbon, even towards the top. So this net cutoff is important because the SDI functions only apply to the net reservoir, as I'll show you. So this is the second of the 3 steps for the masterclass. We need to pick the free water level because our SDI is based upon the free water level, not on true vertical depth subsea. But this can very simply defined using BVW. So you plot BVW against depth. In this case, it's feet TVD subsea, or you could, as I'll show you later, you can use the core capillary pressure. Now, as BVW ignores the porosity, permeability, and lithophase variability, it will give you a very simple curve. So even though in these 4 wells, I've got a lot of variability, when you plot them on this plot, you get a curve. And this defines your free water level. So the trend gives you free water level. But as this curve goes on forever, then we take the highest porosity we see anywhere in the reservoir, and we say that is our free water level. So in this example, the free water level is 903 feet TVD subsea. So that is important. Now, let's get into some mathematics. We're going to calculate our BVW function for your reservoir model. And I'm happy to do this for your data sets after the masterclass. Now, BVW is a function of height, AH to B. It's an exponential function. Now, what do we remember from school mathematics? If we take the logarithmic of both sides, it turns into this equation here. We go from an exponential, when we logarithmicize it, it goes into a linear equation. Now we can show that on a cross plot. This is real data from the North Sea in 6 very different reservoirs, very different environmental settings, different fluids. And what we see is that on a log-log scale, as we expect, all the core data has fallen on a straight line, right? So if we wanted to derive a function for these fields, in actual fact, a straight line can be defined by 2 points. So we only needed to take 2 core and good core points from these reservoirs to derive the SDI functions. But what you notice is that these lines are parallel. So even though we're looking for 2 constants, A and B, the B is actually the same between all of them. It's 0.42 perhaps. And yes, the answer is 42. This gradient is scale invariant. So you can change this axis from capillary pressure to feet to meters, and the gradient will be the same. Now, the difference between these depends on the average pore geometry of each of the fields. And as I'll explain later. So this is how we calculate our BVW function. So this is the last main slide of the masterclass. We're plotting our BVW against height or capillary pressure above the free water level, which we've defined. We only plot the net data, and we plot it on log scales. So the complexity goes, it's a simple curve. It's simple, and the curve in log space is a straight line here. Now, as the resistivity log can be adversely affected by thin beds and conductive shales, you should only plot the data from the center of thick beds. And I'll show you a plot of this later. So you really only need two good points, say middle of this bed here and this one, to define the curves. So this is the last one of the masterclass. We want to derive A and B. We've converted to log space, and we've got this linear equation. We fit a straight line regression through your data. Now we use the statistical method y on x rather than default y. So we use x on y rather than x the other way around, because we're predicting BVW rather than the y-axis. There's statistical reasons for that, which I won't go into. So you just derive this straight line here. It will give you two things. It will give you a slope. In this case, it's 0.49, and it will give you an intercept. Now from these two, it will give you directly our B here, but A must be goes to the power of 10. So I will be doing that in the individual data sets for your fields. Right. So let's have a look. We've done a number of studies from academia and from different oil companies, and we took these fields and we said, what is the difference in the SWI functions, particularly the BVW function, between these fields? Now, these fields have got varying permeability from 2 darcies down to low darcies, and the porosity varies. And again, we've got many different types of reservoir, aeolian, fluvial, and so on, and different kind of fluids. So in this complexity, what does the BVW function look like? This shows the per-perm plot. Generally, as porosity increases, the permeability increases as well. So let us compare the results from these fields. So we're comparing the transition zones, how the bottom water changes with height. Now, if you have an ideal field, what does an ideal field look like? An ideal field would be of high porosity, because that would mean there'd be lots of pore space for the hydrocarbon. An ideal field would have very high permeability, because that is the conduit to flow of the hydrocarbon to the wellbore. But also an ideal field would have an SWI function towards the left here, like the gray one. These are the SWI function from the different fields shown in the different colors. The one on the left is the one we'd ideally like to see. And the shape of this is related to the overall pore geometry of the field rather than the porosity or permeability alone. And the BVW function quantifies the pore geometry with the parameter A. Now, let us look at the data from these many fields plotted on 2 cross plots. On the left-hand cross plot, we've got BVW against the height of the free water level for the electrical logs. So these curves here, again, straight lines in log space, each one for a field represent the data from the free water level all the way up to the top of the reservoir. So there's a different color for each of the fields. Now, we've also got core data from those same fields. And here we're going to plot the bulk volume of water against capillary pressure. And what we notice is that the BVW function from the small core plugs as well as from the complete reservoir is exactly the same. Whether it's irrespective, it's derived from the logs or the core data. And I will explain this because we have found it is a fractal distribution of core capillaries. So what to say here to remind you is that over the complete reservoir from the logs, free water level to the top, we get these curves which have a very similar gradient and a separation due to the average pore geometry in those fields. And then we got the core on the right, which is the same. Now, can we believe our BVW function? We need to do a beauty contest. We need to convince ourselves that this BVW function is working. So how are we going to do that? What we're going to do, we're going to derive water saturation from the resistivity log shown in black here. And we're going to derive it from the BVW function shown in red. And we're going to compare that with the core water saturations. Now, these core water saturations, this comes from a field in the Middle East, are high quality. What I mean by high quality, they are Dean and Stark water saturations. The wells were drilled with oil-based mud, and they were doped to identify any mud filtrate contamination. They were cored above the free water level, where the capillary-bound water is immobile, and only the center of the core plugs were sampled. So we're confident that these blue dots represents the true water saturations in this field. The CPI is shown on the right. Now, what do we interpret the results as? We see that the BVW function matches the core data. The resistivity log doesn't. That is because the resistivity log is adversely affected by conductive shales up to 30 feet away. So it finds it very difficult to give water saturation in the center of thick beds and close to bed boundaries. So let's have a look at the water. The water is important. You probably remember from your university work that H2O is 2 molecules of hydrogen and 1 molecule of oxygen. But you probably didn't realize, many didn't realize, that it's actually as a boomerang shape. And it causes the molecule to become polarized with a very negative side and a very positive side, which has a dramatic effect in our reservoirs. This causes the molecules to be very strongly attracted to each other and to the surface of the pores in the reservoir. The electrostatic force shown here is 10 to the power 36 times greater than the gravitational force. And these are the two forces which will be competing in the reservoir, as I'll show you. Now, the water was in the reservoir first, when it was laid down. Later, hydrocarbons migrated into the trap, and the buoyancy forces exerted by the lighter oil pushed the water down to below the free water level. Now, not all the water was displaced. Some of it was held back by the capillary forces in the pores. Narrow pores with smaller pore throats and a larger surface area held onto the water the strongest. And this is a capillary tube. And you've seen this, and the water rises up inside the capillary due to this massive electrostatic force, and has this characteristic meniscus. But you probably didn't realize the meniscus is actually bigger on the outside of the capillary tube because the surface area is bigger on the outside than the inside. And you probably noticed that if you have different capillaries, the smaller capillaries pull the water up the most. In the reservoirs, we're actually looking the other way around. This old reservoir originally contained water. As the hydrocarbon entered, as represented by the area, it pushed down the water, and the water was held depending on the size of the capillaries. So the smallest pores and pore throats hold on to the most water. And consequently, hydrocarbon requires more pressure to enter the small pores. I won't go into this. It's in the notes from this masterclass. But this is the equation for the capillary pressure equation. This is competing with the gravity, and this is the equation for the competing gravity, also effective upon the water. So the force of gravity on a column of water is determined by the difference between the oil and water densities, and this is called the buoyancy pressure. So the water at a given height in the reservoir is determined by the balance between these two forces, the capillary forces holding up the immobile water and the force of gravity pulling that water down. Now, the hydrocarbon can only enter the pores that the water doesn't want because it's got the stronger force. So in the well and in your reservoir model, part of the pore space will contain both oil and water. And generally, this is where the idea of water saturated came up, the percentage of water in a pore volume. So let's have a look at these two forces on the reservoir fluids. Now, the capillary bound water comprises of a continuous column of water in the oil leg. So you've got the water in the oil leg held onto the pores all the way to the top of the reservoir. The oil is in the remaining pore space and is also a continuous phase, but it's a lower pressure. Now, although the oil and water are coexisting in the same localized rock, the pressures on the two fluids are different, as shown here. Now, the formation pressure tester only measures the mobile phase. So it will only see the hydrostatic gradient below the free water level, and it will only see the oil pressure gradient above. And this is why, surprisingly, it's a straight line. The intersection of these two curves is the free water level. So the buoyancy pressure, which is the difference between these two curves, increases with the height above the free water level. As the buoyancy pressure increases, the oil phase can displace more water and enter the smaller pores. Therefore, the water saturation is expected to decrease with height above the free water level. But as I showed you before, this is not always the case. Now, fractals are very useful in reservoir modeling. Let me go over fractals with you. And this is why the BVW function works. What are fractals? We see fractals everywhere. We see fractals on the small scale in snowflakes, and we see it in vegetables like the Roman cauliflower. We see fractals on the big scale, like the Himalaya. Each of these ridges has a certain shape, and as we zoom in, you see the same shape on the smaller ridges all the way down to the valleys. You also see the same shapes radiating out from river channels. This is a photograph I took when I flew into Basra to give this presentation. Now we even see fractals on the really big scale. This is a picture of the cosmic microwave background from this book here. Now, if we zoom in on the cosmic microwave background, which was the leftover from the Big Bang, we see certain patterns. Now, these patterns actually became galactic superclusters. And as we zoom into those galactic superclusters, we see galaxies. And all these galaxies, all the way up, are the same shape. Now, a fractal is a simple repeating pattern. So we see fractals on every scale in the universe. It's a never-ending pattern. They're infinitely complex, but they look the same on every scale. This is a Mandelbrot diagram you may have seen. And as you zoom in on this, you will see a simple repeating pattern. Now, this is going to be very important for reservoir modeling. Other names for fractals are self-similarity or scale invariance. Fractals are important. Let me show you another example of fractals. They're objects which are similar except for scale. So let's look at this tree. If we look at this tree from a distance, we see this overall shape. As we move into the tree closer, we see this major branch, and it has the same pattern as the overall tree. And all the way down to the smaller branches, all the way down to the twigs, we see the same repeating pattern, right? Now, there's a reason for this. This is because the tree comes from the DNA in the seed, and the seed has a very simple instruction. It says, grow a bit and branch, grow a bit and branch. And from that very simple mathematical instruction, it is able to build something which is huge and beautiful as a tree. And I'm going to show you, this is even more important for hydrocarbon reservoirs. But how do we verify if something is fractal? The coastline of Great Britain has been claimed to be fractal, meaning that however close you look at it, you see the same repeating pattern. So how can we prove that? Well, let's have a look at the length of the coastline, N. Now, to determine the length of a coastline, we need a ruler. So we have a ruler here shown in purple, and it determines a coarse estimation of the length of the coastline, shown here as 9 units. Now, if we decrease the size of the ruler here to a red ruler, we can go into those estuaries and we get a longer coastline. And if we take a smaller and smaller ruler, we get a more and more accurate estimate of the coastline. So let's have a look at one of our favorites, the cross plot. Now, if we plot the coastline of Great Britain as determined by our ruler, against the ruler, again on log scales. So on this scale here, we've got the length of the ruler R. And on this axis, we've got the length of the coastline determined from that ruler. These are the different colors, these from 4, and they're plotted here. And what you notice is that they're all on a straight line. And this line gradient is the fractal dimension. So mathematically, it can be shown that if something falls on a straight line on a log-log plot between its ruler size and what it's measuring, it's fractal. So however small a larger ruler, you get the same answer. Now, we're more interested in reservoir rocks. If we want to know porosity, we can take thin sections of reservoir rock and we can image it using a scanning electron microscope. And this is the result here. So this is a slice of the rock with a scanning electron microscope. Now the white bits are the porosity. Now we can calculate the porosity of this rock by simply adding up the number of white bits. Now, each of the white bits is represented by, the pores is represented by a pixel, which is white. So we can count the number of pixels. Very simple. They represent porosity. But we've got the same issue as with the coastline in the United Kingdom. If we go for smaller and smaller pixels, we get larger and larger estimates of the porosity because we see the smaller pore sizes. So this has been done in many studies. If you plot the pixel size, the size representing the porosity, white, against the calculated porosity as it changes, you get a straight line. This is a Berea sandstone. It's a straight line, and it proves that reservoir rocks are fractal in nature. They're a very simple repeating pattern. Now, if they're a simple repeating pattern, we can express it mathematically, and we can use that in our model. Now, I won't go through this slide in detail because it's in the paper, but this is the relationship between the porosity size and the radius of the capillary pressures. And with some mathematical movement, you can actually derive the equation, the BVW SWI equation, shown in red. I will continue now just for several more minutes, and then we'll stop for questions. The BVW function also gives us a differential reservoir model. If we calculate our water saturations here from the resistivity log, which was acquired yesterday, and compare it with the BVW function, there's a difference because the BVW function represents the initial charging of the reservoir. There is a difference in the water saturations. So in this interval here at the top, there's a difference between the resistivity derived SW, which was logged yesterday, and the BVW function, which was acquired from the initial charging tens of millions of years ago. There's a difference, and this shows that this interval has been swept. But lower down, the water saturations from both methods are overlain. This shows that this interval needs to be targeted because it's got residual hydrocarbon there. Notice the resistivity log is incorrect in the thin beds and also close to bed boundaries. The BVW function is correct in the thin beds. This is because the BVW function ignores the thin beds, bed boundaries, and shales. Now, we can actually use the function to identify the hydrocarbon water contact. Remember, this is a varying structure throughout the reservoir, depending on the local porosity and permeability, where the free water level is a constant plane, right? So as SW is equal to BVW over porosity, we can actually make this cross plot, and we can go back to SW space. And what you notice, you get these characteristic curves for each of the water saturations, so multiple. So this will actually give us the hydrocarbon water contact for different porosities. So a part of the reservoir, which is only 5 porosity units, this is where the contact will be hundreds of feet above the free water level. Whereas at 20 porosity units, it's the free water level and the hydrocarbon contact are very close, as we expect. Now, the BVW function can be used for depth control. Depth is our most important petriphysical measurement. Now, the true vertical depth subsea can be out by plus or minus 30 feet due to different errors. Now, this can be very significant if we want to calculate the hydrocarbon in a reservoir. Now, if we're confident that we're looking at the same compartment, because of the produced hydrocarbon and other methods, we can actually use the BVW function to normalize the depth between different wells. So we say the free water level is constant throughout the wells. If there's a difference, it's because the depth is wrong. Now, in a recent study, we calibrated the well depths to the free water level, and this changed the equity between 2 oil companies by 3%, which was billions of dollars. I want to just show you a couple of more slides before we go to questions. I want to tell you about the irreducible water saturation, which we forget about. This is the lowest water saturation that can be achieved in a core plug. It is usually achieved by flowing hydrocarbon through a sample or spinning the sample in a centrifuge. So the SW irreducible actually depends upon the dry pressure or the centrifuge speed. The water saturation therefore depends upon the item of the free water level. There is no minimum water saturation. There is no SW irreducible. So we can forget about that. In the model, we we want to calculate the hydrocarbon in place. We do this by averaging the water saturation in each of the cells and then add them together to give us the hydrocarbon in place. Now, it's essential when you're doing averages in the reservoir model is that you pour volume weight the water saturations. And there's more information about this in the paper. And also, the BVW function is very useful for uncertainty modeling because you can calculate a P50 case, a most likely function, but you can also calculate an upside and a downside function by partial differentiation of the saturation equation. And there's more information on this in the paper. Now, this is important because you can give to the reservoir modeler 3 SWI functions. They can calculate 3 different hydrocarbons in place for the reservoir, which the client is very happy to know the uncertainty on the reservoir. So, last slide, the conclusions. We have derived a BVW function from the fractal nature of the reservoir rocks. It can be derived either from the electrical logs or from core data by simple linear regression in log-log space. The logs and the core will give you the same function, and this has been shown and is very useful, is because this is a QC of both. They should give you the very same result. If they don't, you need to look at your data again. Because the same on the same scale between a core plug and the reservoir, this confirms a fractal distribution of the capillary pressures. The function defines the net cutoff and the shape of the transition zone. It determines the free water level and the hydrocarbon contact. Importantly, it is independent of rock characteristics. It's independent of facies type, porosity, and permeability. And you can forget about thin beds, bed boundary effects, and shaliness. So it can be simply implemented in your reservoir model. And the key conclusion is, this is the plot to make. Forget about water saturation. Think BVW. Thank you. I'm open for questions.
Thank you, Steve. We have a few questions in the chat. I'll read them sequentially. There was a question about A and B constants, which I believe has been answered in detail. Okay, the first question comes from Sanjeev Kalita. In case of a thin layered reservoir, where free water level is not established in the drilled wells, how to take the free water level? You're muted.
Sorry, can you say, it's a thin bedded reservoir, yes?
In a case of a thin layered reservoir, where free water level is not established in the drilled wells, how to take the free water level? I assume how to take free water level using your approach.
Well, this is where you will see the water saturation is very dramatically. With the thin beds, it will be very difficult to pick them, and therefore I would recommend that you plot the BVW against the depth in these wells, as the BVW will take out any lithofacies variation, and also it will if you just look at the thick beds where you've got no effect on the resistivity from the bed boundaries, it should actually help you pick the free water level. But you should not only pick the free water level just from the logs. You should also pick the free water level from the pressures. Now, if you've got pressures, because it's a straight line in the oil space and a straight line in the water, they should also give you the same free water level as the prediction from the BVW curve. And I'm willing to discuss that particular example of thin beds post masterclass. Yeah.
All right. The next question is also from Sanjeev Kalita. How to get A and B values from electrical log points?
Right, that is the essential part of this masterclass, right? You can get it from the core data or from the logs. Today I showed you from the electrical logs. First of all, you need to determine your net cutoff, because the BVW is equal to the porosity in the non-net. But where the porosity is sufficient to old hydrocarbon for the pore entry pressure, for the hydrocarbon to enter the smaller pores. That is net reservoir. And so you first of all derive your net cutoff, and all subsequent plots only plot net data. Now, so the next plot, it would be to plot your SW against height above the free water level, to confirm that you've got a lot of variation. And by using a z-axis, you can determine the variation by different zonation, by different lithophases, by whatever. And then by changing to BVW, you can confirm that the BVW takes out the spread. And we can look at your particular example after the masterclass. Yeah. Then the last step is then to convert the BVW and the depth to log space. And in log space, we have got a straight line. We only put the line through the best points because the resistivity log is most confident. We get two parameters, the intercept and the gradient. And from the intercept and gradient, this will give us the A and B. And we can use that function completely throughout the 3D model.
Thanks, Steve. You can also go to the slide if it helps you to answer the question.
Yes.
Next question comes from Ahmed Wakas. Capillary bound water is higher in fine-grained phases simply due to the larger surface area available for the wetting phase. How does bulk volume of water remain same for different phases type?
Right. Right. The key thing is to remember is that the water was in the reservoir first. The reservoir was just contained water originally. Later, it was charged by the influx of migrating hydrocarbon. Now, it was a very simple balance between the capillary forces, electrostatic forces holding the water in place, and the gravity pulling down. So the water, the water was there first, and the hydrocarbon could only enter the space which the water didn't require. So what we find is that if it is above the if the porosity is above the cutoff, the hydrocarbon saturation will reduce and reduce, and it will give you a precise saturation for the fine-grained, for the low porosity rock. And it's probably best to look at one of your wells for that. Let's see, we got a good plot of that one. So, you from aku tak tahu dia pergi. Ya. Balik lagi buat ni.
Don't say Steve, just a moment.
Alexander Bilevich, WhatsApp audio.
Hello there.
All good, Steve. I can see you.
Right.
You're disconnected, right?
Yeah, sorry about that, disconnected, but we're back in again. And as I say, we're going to be looking at lots of reservoirs, and I'm very happy to work on your data set after the masterclass. But if there are any general questions which would be of interest to the audience, I'm happy to answer them now. Yeah.
Yeah. So there is a related question. If connate water is replaced by hydrocarbon and it does not replace all the water, why there is no swirl then? I think it's referring to your statement earlier that swirl is an ever-changing value.
Yeah, the swirl is the irreducible water saturation. The reservoir modeler tends to think the water saturation decreases until it gets down to a minimum, say 10 or 20%, and they need that for their reservoir model. But capillary capillary core analysis shows that the water saturation decreases indefinitely. So if you've got a very thick reservoir, water saturation will get very low. So the irreducible water saturation doesn't really exist. The water saturations decrease indefinitely. And it's more probably better to think about the bulk volume of water. The bulk volume of water, as I showed you in that depth plot, will continue to decrease with height, or it will decrease more and more you spin a core plug, more water you'll expel. So the BVW will decrease with height and with centrifugal force.
I think a great example of that is the MICP plot, right? Yeah. At 50,000 psi. Next question. Will bulk volume of water change in a mature oil field with depleted reservoirs where hydrocarbon contact has been shifted up?
Now, this is where the BVW function is liked by the reservoir modelers. Now, the BVW function actually represents the initial charge in the reservoir. Before any movement, it will show you original paleo contacts. It will show you how the hydrocarbon and water were divided before the reservoir was produced. Now, you compare that with the water saturations that you derive from the resistivity logs, which were logged yesterday, gives you a different water saturations. So the power is by comparing the mature reservoir with the original reservoir, you can see which intervals have been depleted, which ones need to be swept. It shows you what the irreducible oil saturations are. So there is immense power in looking at the BVW. The BVW is the original tens of millions of years ago, where the resistivity log was the log which we did last week.
All right, next one. This one is similar to what I also was going to ask you. Regarding use of core data, are you referring to scale data or Dienstag data?
We use the best data possible. When I showed you the plot of water saturations from core, that was Dean and Stark water saturations. Yeah. When we're dealing with capillary pressure, then these are the measurements of capillary pressures against the bulk volume of water. Remember, in the core laboratories, they do not measure water saturation. They measure the amount of water dispelled under different pressures. And then if you want SW, you have to divide by the estimate of porosity at those depths. Yeah. So we use the quality data, yeah.
So basically you're saying if you have swirl from centrifuge, you can use that to multiply by core porosity, right?
Yes, if you multiply your water saturation by your porosity, you get BVW. The water saturation is the percentage of percentage. It's percentage. First percentage is porosity, and then it's percentage of the porosity. So SW is a percentage of percentage, and if you remember from your school mathematics, very strange things when you start dealing with percentages. Yeah. So, for instance, you wouldn't develop a field or perforate an interval because the water saturation was 50% or 30%. You would have to know also what the porosity was there. So that is the important factor, the amount of hydrocarbon. So a cutoff for water saturation for perforations doesn't lead anywhere.
All right, next question. Is this method applicable in complex carbonate reservoirs with bimodal and trimodal pore systems?
Certainly, it's been run in many Middle East fields for the major operators there. It works in complex carbonates, and it is valued in complex carbonates because it takes away the variability due to the different lithophases from dolomite to limestone. Provided that overall there is a relationship between porosity and permeability. It needs a relationship there, and it works. But basically, you just make the plot. You've done all the hard work is acquiring the logs. You've done all the petrol hard work is depth shifting and calculating your SWs and porosities. So you make a cross plot, the powerful petrophysical tool. We make the cross plot of water saturation against porosity, as I showed you, and then you change this x-axis with one click to BVW. If in your carbonates it improves the relationship, then use it. Yeah. Cross plots.
Next question. This one is a long one. Hi, the saturation comes from unknown user. Hi, the saturation height data is also required as a part of the input into the dynamic models. And the standard input formula is J versus SW or PC versus SW, which is used along with relative perm data. Can the data set in terms of BVW be denormalized for a given rock type or rock types? Or are there any better way of handling this in a dynamic model? Do you want me to read again?
No. I think it's going to be it's really beyond petrophysics. We're looking at the dynamic model there, and I can't answer all the questions about the dynamic model, but where the dynamic model requires an S to be irreducible in the software, then we recommend, if they need it, they use the value of SW at the highest point in the reservoir. They also like to use the J function. Now, Leverett agreed with the BVW function in one respect. He said that all of the reservoir acts as a single capillary, surprisingly. So you can do analysis on simple core plugs and you'll get the same results. You can imagine sending away a little core plug like that to core laboratory, and it comes back with a function, whatever, Leverett J function or a foil function. And the operator is going to say, how can I believe that the function from that small core plug can be used in my massive reservoir? And you can say, because we can prove it is fractal. What is working on the small scale is identical on the big scale. If you go and look at an outcrop of rock, you see that the porosity and permeability is varying just a few centimeters from each other. And yet you say, well, how can the reservoir modeler model this reservoir, which is hundreds of kilometers in volume? How can you model it when it varies so much? And this is because of the fractal nature. So I can't answer the full question on that. We'd have to speak to a reservoir engineer. But where I've come across this, we've got agreement with the J function. It works with the J function. And we've got a SW irreducible. Now, the problem with the J function, now I'm an independent petrophysicist, and when the client asks me for an SWI function, I give them all the functions. I give them a J function, a Skelton function, a for function. I say, I am the worker. You can choose this. Your reservoir modeler can choose which to use. And what they tend to use at the end of the day is the BVW function, because the J function needs permeability as an input, and permeability is very difficult to map throughout the 3D model.
Thanks, Steve. Next question, also a long one. What I find difficult, it comes from Vineet Kumar Munt. My question is, what I find difficult in BVW approach is the following. The sheer issue of being prone to error, higher number of data points if logs-based BVW is used, and wide variation. Generally, BVW is a very low number, between 0.01 and 0.1 normally. So slight change in the assumption of a constant BVW, like 0.04, 0.05, brings a huge change in SW estimation on a field scale. Higher uncertainty, hence a bit difficult to rely on. And he gives an example of calculations. I'm not going to read them out.
Yes, we've looked at many fields where we have the problem with very low BVWs. And the question is, how can you fit a curve when you've got such low values with the corresponding error bars? Well, the answer is, first of all, we're moving into log-log space. We're plotting BVW against height above free water level in log space, and therefore we know we're looking for a straight line. And a straight line can be defined by just two good points. So we've got in our reservoir the problem of low BVWs, but in that reservoir we may have a thick bed. We may got two thick beds. We only need the measurement of the BVW in the center of those thick beds, well away from the effects of the resistivity log on conductive bed boundaries. We use those two measurements to predict and derive our BVW function. And that function can then be applied everywhere through the model, including the parts of the reservoir which has got very low BVW. It's the same function. But how do we know that is correct? The client says, how do we know it's working there? Well, we take quality core data, Dean and Stark water saturations, and we show that the function is matching up with the independent water saturations from Dean and Stark. So the answer is, we've got a lot of scatter, but we get away from the scatter by only taking two good points. Obviously we include the points in the cross plot, so we can see that generally they're consistent, but we only take the centers of two thick beds to do it. And in the future, we may only need one bed, because it seems that the B is the same for every field in the world. Fractionally, it is very simple, and we only get differences between reservoirs with the A parameter. Some people say, well, if it's independent of lithophases, why do you get a different A in one field and another? It must be because of the different lithophases. No, it's because the average lithophases, the average pore geometry in one field gives you the A, and it gives you a different A for another field. That's why you've got different lines with the same B. Now, if those fields could hypothetically be brought together over geological time, they would merge to have the same A value. So we've got one B throughout all our fields, and the A varies depending upon the local pore geometry, which is defined by the BVW function.
All right, this is the last question in the chat. Comes from Willie Tan. If wells are only drilled close to the crestal part of the structure, where SW is close to SWR, and no wells drilled close to the transition zone, how reliable can we use the FOIL function to predict BVW in the transition zone?
Yes, this is a major problem, is where we've drilled wells and they're well away from the free water level. towards this crest of the reservoir. But we need to know the free water level. And if you don't penetrate it, you can't use your formation pressures to find the intersection for the free water level. And also, because it's so far away, you can't use the predictions of the water saturations because everything's showing hydrocarbon. But what you can see a trend. You can see a trend on the BVW, which is steadily increasing, as I showed you, with depth. And even though you might not penetrate the free water level, you can predict what the free water level is roughly. And in actual fact, a precise measurement of the free water level is not essential, provided your function matches the data towards the crest. And I could explain that later, which is part of equity studies. So that is a real problem, yes, sir. So I think that we could discuss that later with your particular data set. So I'm happy afterwards to look at data sets, you the work, the number crunching, but I'll be looking at the plots and help you derive a simple and convincing BVW function for your reservoir model.
Thanks, Steve. So we have another 5 minutes left and no questions left in the chat. I'll ask you a question. Can you go to your net reservoir example slide? It's a very interesting example. Where you have the net flag, net reservoir flag in blue. It is number 22, slide 22. Yes, the slides will be shared as is the record of this presentation.
Right. Okay.
Right. So the approach, one of the steps in the approach says that there is a netting exercise based on porosity, right? So this flag
to calculate the net based on the porosity, yes.
Right. So in this specific example, the bit between the dash line and the base of the net, where there's non-net, where the arrow points at the bottom.
This down here.
Down here, yeah.
Or this, the bottom one. You've got non-net here above the free water level, and you've got non-net here, here, and here.
Right. So at the very bottom, next to
this one here.
Yes.
Yeah.
The porosity is quite high. So
that's right. The porosity is quite high.
So it seems like not just porosity was used to cut off this, right? Because this was first cut off, and then you did the BVW.
That's yes. I did show you in the previous. Was it this? That the actual net cutoff does actually vary with depth. That's why in this case here, you've got, it's non-net because it's close to the free water level. Now, in my masterclass example, I said use a net cutoff. Well, where we're using it where it's over this interval here. We're using it. It's kind of the first estimate for the net. We're saying that anywhere where the what was it net? A net one as well. This one here. Yes. So in this case here, we want to, the net cutoff is where we're sure we've got no hydrocarbon, and we've plotted like here. But the net cutoff, as I said on the other slide, is actually varying with depth. Yes. But for the purposes of deriving the function, we only want the very best data. So we're not bothered that near the free water level we have got some hydrocarbon. We want the very best, and then we plot the curves, we derive the function, and then the function is valid everywhere because it takes account of the varying net cutoff.
So the reason this is non-net is because this rock indeed has high capillary bound water, not because it's a transition zone, right?
Let's come back to that one in 20. You said.
Just a second.
Yes. Say that again.
Yeah. So the reason this is a non-net is because this is indeed a high capillary water sand, and not because it's a transition zone, right? Because it's just it just happens to be next to free water level.
There's no transition zone. This is non-net because the capillary bound water is equal to the porosity. So when BVW is equal to the porosity, that is fully water saturated, and you will get this just above the free water level,
right?
Because this is the shape of the BVW curve there. So as we get closer and closer to the free water level, we will get more and more net. Net, remember, is the ability to hold hydrocarbon. Now down here, the water is taking all the pore space. So even though the permeability and porosity is very high here, the water it will not give up any of its space to the hydrocarbon. So it is incapable of holding hydrocarbon and is non-net. Yeah.
Thank you, understood. So it's a low perm rock, basically.
No, this is very high porosity permeability, but it's close to the free water level. Like the net cutoff changes. So as we get closer to the free water level, the net cutoff goes from 5 porosity units up to 15. So even if it's very good quality rock, the electrostatic forces are so great, the capillary forces are so great that there is no entry pressure for the hydrocarbon. Maybe we can discuss this later.
Sure.
Example. But for deriving the curve, we need a cutoff. So we just use a cutoff from up here where we're trying to get the best match.
Thank you, Steve. Understood. So I guess there are no more questions. Thank you, everyone. Have a great week ahead.
Thank you. Yeah, and please get in touch. And I want to look at some difficult data sets so we can refine our parameters. And yeah.
If you will write down your email address, right, for which they can contact you.
Yes, it's on LinkedIn email address in my contact details, or they contact me via messenger there. And yeah.
If I'm not mistaken, your email address can only be seen by those who have contact, like your direct contacts. I may be wrong.
Yeah, I've got, yeah. So the first level of contacts, yes. So I will be giving my email address. It's steve.cuddy@btinternet.com. I can type it in there, can't I?
Yeah, we'll do that. No rush.
Oh, you'll do that. You put my yeah. I'm looking forward to seeing some difficult data sets. Yeah, well, thanks for the invite. Yeah. And the presentation will be shared as a PDF, and I'll be getting information about the award-winning paper on the subject, which goes through the mathematics. For those who are interested in that, and yeah. Well, that's 9:30. That's a good go. Yeah.
Yeah, let's probably stay a little while and then have a short discussion.
Yeah, it's best to answer some of the questions with a plot, and